Hi folks, Mr. Teslonian back here again. Today what I'm going to do is make a very unique style Tesla turbine design. What we're going to use to do this is these stepper motors. These stepper motors have a bunch of teeth and they have a stator and a rotor in there. The stator is the part that sits on the outside like this, holds all the electromagnetic coils around it. So there's one of the stator rings still in there. These would have had the copper wire coils. I have some of the copper wire sitting right there, wrapped all the way around, and the rotor would have sat right inside the center of that, which this piece right here is the rotor. And we have one of those stator rings sitting down there on that rotor. What we're going to do is use these laminates, which is what they're called. It's a laminated little sections of steel that are all pressed together. It gets rid of the eddy effects inside of electromagnetics. We're going to take these, now that I've separated them all, and we're going to build a little tiny Tesla turbine that should produce incredible amounts of power because of all the little teeth that are all over on these things. So we not only have a bunch of teeth and little blades and exterior teeth in 4 positions, internal teeth right here on each one of these. We got some blades in here, but we also have teeth here on the rotor. So let me pull that ring off real quick so you can see the rotor. I had to chip out, so you can see this white material here, it's like an epoxy material, was filled all the way through each one of these little teeth. And if I give you some angle there, you should be able to tell just how deep each one of those are. You see some of it still chipped, needs to be finished off with the Dremel tool now. So I had to chip out all that material in those teeth to get it, so I had some recessed grooves in those. This will actually be where the center of the tornadic effect, or the tornado's cone down focal point, will grab against. So all that pressure, that energy being squeezed down, will grab into each one of these little teeth here and help deliver a lot of that energy out the drive shaft, which is right here. We have a couple set of bearings already on there, and that'll help deliver a lot of that energy out. Now with these rings, so what I'm going to do is now permanently mount all the stator rings down on this. Let me give me a second here to kind of line a piece of that up on there, kind of. Alright, if I can get that nice and even on there, you'll see what I'm going to do here. This will be basically a bunch of laminated rings once again, but like a Tesla turbine, we're going to have a little thin gap between each one of these rings. So there'll be a thin boundary zone or boundary layer right there between each one of them, allowing the Tesla style design, the Tesla turbine style design, to function properly. And what I'm going to do now is line each one of these up. So I'm going to start out with all the teeth on the internal rotor here and the external ring to line up, so there's an output hole in each one of those. You notice how nicely it creates that air grab area right there at the center, where all the energy is coned down at the very center of a Tesla turbine, where normally you've got very thin or no blades at all right there in a smooth center. This will help grab a lot of that. So you get energy out here on these outer notches. You're going to get energy delivered here against these. You're going to get energy against the blade and the boundary layer effect against the surfaces. So one of the things now, what I got to do is permanently mount all these rings with a little bit of a gap between each one of them. So I'm going to use probably a thicker construction paper or something like that that's going to be made out of plastic to separate each one of the layers of the rings all the way down this. So I'm going to go from this side all the way down the center here to the other side and just stack a bunch of these external stator rings. So these were that ring, like I said, that were sitting inside of here. I busted them all out, took the wire off of each one of them. Now the next part of this is, instead of each one of these rings being lined up with the next, so here, see if I can give you this. Instead of being lined up like this, what I'm going to do is stagger, just like that, each one of the rings. So the next one will be staggered, the next one will be staggered and staggered. Nice thing is I'm going to line them up right with the teeth here, so they'll be a pretty even staggering all the way around. Easy to monitor your staggering. Instead of lining them up so there's one big gap, just like this, all the way down the centers of them, where you can see my finger here behind the hole, I'm going to make sure there's a bunch of staggered blades, like a spiral staircase basically, going all the way up this thing. We're going to do that until we get all the way to the top. It's going to take me quite a while to get this all mounted, glued into place, everything's set so it's hard mounted in there. The next step is I'm going to have to put this into a table where I can spin it nice and fluidly without any wobble or anything. I'm going to have to set up a grinder because I need to remove just a very fine amount of this outer edge right here to fit that back in this case. So what I'm going to do, once that is set up, we're going to mount this back inside of that case and touch the sides way too much, so they're not going to give you any rotation without grinding. So I've got to do a little bit of work on the outside, but I'm not going to do that until I get it permanently mounted. And like I said, I'll just spin that next to a grinder on a solid platform, even it all out all the way around, and move just enough material to give me enough rotation or air gap just so these will rotate without touching. Once we're done with that, we're going to put this all back into the case, So we'll use the original stepper motor case. We're going to put it all back in there. We're going to drill some holes for the air input and the air outputs at the centers here, right around where the bearings are going to be. The nice thing about this is the outer rotor right here is going to be right about where the air output holes for this engine are going to be. So right here, right around that outer ring that holds the bearing right here, it'll be the air outputs. And we'll put an air input into the side of this outer case just like that. So let me get that done and I'll show you what it looks like. Alright, so what I'm doing right now is I'm about halfway done with our Tesla turbine here. I want to show you how I'm keeping these so they'll never rotate around the center of that shaft there. And right here, you notice that little tall pin sticking out at the tip of my finger? Right there, if you can see that. And there's another one right over here. These are keeper pins. And they're just big enough, I had to shave them down with a grinder. They're just big enough to slide down inside of these channels and still line up with, let me zoom in for you. Still line up with these teeth on the other side, the outer stator ring teeth there. So I'm pushing that down, I glue them into place, and every time I stack a new ring, I offset by one tooth. And right now, you should be able to, if I tilt this, you should be able to look through those. So you can see there's a air gap going all the way through the spiraling like staircase look right here at the tip of my finger. So I'm staggering each one of these blades, just making sure that this turbine has really a turbine style blade system in it. It's not only a Tesla turbine, but it has also a normal style turbine in it. How I'm spacing, you can see here down below, you can see the red wire. I'm spacing each one of the rings right against the center here with a piece of this copper wire that came out of there. And I'm just wrapping it all the way around. And then I push down a new ring. And right now you can tell I have to add another piece to this to keep going. But I just got to the halfway marker there. So I'm ready to go. I got my new keeper pins in there. And that'll make sure these rings never slide. Once you slide those down over these keepers, that's going to make sure these outer rings don't slide against the inner ring here. So I'm going to go ahead now and keep wrapping that copper wire around the center in between each one of the layers. I'm going to finish the second half of this and I'll show you what it looks like when we've got the entire thing done. Alright, so now that I've completed the entire rotor, I just want to go over it with you real quick, show you what it looks like. You can see the staircasing line going up the outside edge over and over again, all the way around it there. That is one of the advancements that I'm doing to the Tesla turbine, and that is because the outside edge of this was typically very, very smooth, just like in between these lines that you see where the indent doesn't exist. Very smooth, so you had to get to a very high RPM before it started producing the efficiencies that he had recorded. So one of the things about this is these are actually just little indents based on that little notch right there. The tip of my finger, you can see these notches all the way around. There's 4 on each one of those plates. And because each one's slightly staggered off from the next, it makes this nice staircasing look all the way around the outside. Each one of those little edges in there, the front facing edge the air is going to impact, it's a little step to get it going. So we should get a much higher efficiency at lower RPMs, or at lower pressures at least. So the startup torque from this Tesla turbine design should be greater or more efficient than the original design Tesla had. The other thing that's going to advance the Tesla turbine in this design is if I can get the angle just right, you can see down in these holes right here at the tip of my finger, each one of those as I go by, those are a swirling staircase just like what you see on the outside edge, following all the way up here on the inside just like what you see on the outside. So there is 8 individual staircases all the way through this, and like you see on the outside there's actually an air gap just like the Tesla turbine, the boundary zone in between each one of those. So it's not a dead stop. There's actually going to be the turbine style design Tesla had originated, but also with a stepping vortex in the plates themselves or in the bridges of the plates. And I have something kind of set up real quick here just to show you. This would be more like what Tesla had designed. You've got a bunch of the plates stacked together here, and they're not spread apart in any way, but they're stacked together and they'd be all equal in line all the way down. Whereas the advancement here is, once again, there's a stepping staircase design all the way through this, following with the turbine or the vortex effect that's going to take place inside of this. So one of the things here also that we added to increase the potential of the Tesla turbine is, like I showed you in the original creation video, down inside of this is the center rotor piece that has all those little teeth in it that were magnetic hogging points in the stator motor that we used to start this with. And each one of those are going to grab where the vortex gets the tightest inside of the engine and deliver a lot of torque around that inner rotor center there, producing a lot more torque output to the shaft itself, which will increase the potential output of the Tesla turbine design. Now I've got 2 more of these I'm working on that are different patterns also, designed to do different things. Each one has a different potential for either medium, low, or high RPM outputs, low pressure and high pressure outputs. There's even one of these that I'm producing right now that I'm going to use to generate hot water through motion. So real quick here, let's finish this up. Here's the bottom of the outside casing, and you can see here I've drilled the holes all the way around. If you look on the inside of there, I had to drill them there because of the bearing cup that was in the case there, so I had to match it right on the outside of that all the way around. So we've got our air output holes, and we can do that on both sides, but for now, because of the way this design is, it's going to be better for impacting air at one top surface instead of directly into the center. I'm going to start at the top, rotate the air through the system and out through the bottom. We're going to attempt that first with this design and see how much better that's going to work. The cap here, obviously nothing done yet, but you could once again drill those holes all the way around, which we may end up doing later on once this has been thoroughly tested this way. The outer ring here, I've just got one little hole drilled in it. I've got it dual slope, so I've pivoted it in two different directions. That way I could test both directions for which one would actually follow the cyclone better. There's an obvious path that makes, physics says, you want to spin it this way. But there could actually be a benefit to spinning the opposite direction. You never know that until you try it, so I always leave myself an ability to test things like that, something I'd thought of. Once we're done with this, we can permanently attach the air input or water input or steam input channel onto this that would hold your hose, and that would be finalized. So there's our outer ring. I've honed that out. I've put this in a drill here and just used a grinder pad against it as I spun it in a drill to get that all nice and even. You can see how shiny it is. Let's go ahead and set this thing together now. So I'm going to take the bottom plate, we're going to take the bearing cup, stick it right in there, just like that. There we go. Now because, once again, I want to show you, that outer ring is magnetized. If you just try to stick this ring on there and spin it, it's not going to look like it's spinning right. So you got to put the cap on to make sure you've got your tolerances, but that's going to give a really unique effect later on when we want to use this thing for other projects. So let's put that outer case down around it, kind of set it on there. Then we're going to take the top and put it on there, and there we go. And now we've got a spinning Tesla turbine ready to go. All we have to do now is put our air in right here, or steam, or whatever we're going to use for our power source. I've still got to find another way to clamp this whole thing together. The original screws right here at the tip of my thumb, you can see these 4 screw holes, went all the way through the inner part of the case to the other side. Here is the opposite 4 screw holes, and obviously I can't have bolts sticking through there right now because of the rotor that's spinning in there, so I have to go to an outer bolt design over this, which is pretty simple to do. No big deal, you can figure that on your own. You could even drill through the case here and put a little set screw on the top and the bottom that'll hold it together. You can see the back end of it ready to go, the air output. We can see the air inputs on the top side, so the vortex has to be created all the way through the system, come out the back side here. Next time what we're going to do is try to build some mounts for this. We're going to get our air input set up and make sure it's in the right position before we go on to any power test, obviously. We're going to build a power output system for this, some kind of neodymium generator, a high output generator to hook up to this, so we can really measure the potential outputs from our input. Hope you enjoyed, folks. Until next time, this was Mr. Teslonian. Folks, Mr. Teslonian here. What we're going to do today is test this little vehicle out with our homemade advanced design Tesla turbine as its power source. And the way I'm able to do this is, you can see our Tesla turbine over here. That's the homemade advanced design. You can watch the video on that. This right here is a little electric motor with a gearbox on it. It's got a 13:1 gear ratio. And all I'm going to do is drive off the other side's output right here. So there's a shaft coming out of this side of the motor. Had a little cooling fan that went into those holes and blew air into the electric motor here. There's almost zero resistance in this electric motor since there's no permanent magnets in there, as long as I don't add any current to it. So I'm using the output shaft that went to the fan on this side, which is really easy to rotate to create torque over here on the drive wheel. So this wheel's our drive wheel. Here's our engine. We're going to apply compressed air from our trompe hammer. That's about 150 yards away right now, powering away, giving me roughly about 100 psi at the moment. And we're going to be able to use that power to put in right here, this little hole at the tip of my finger. That's our test hole that we originally set in this Tesla turbine, just to see how little volume truly do I have to add into this to create some kind of torque output. And that's what we're looking for, low speed torque startup outputs, which are really, really difficult to get out of a standard model Tesla turbine. They need to hit a very, very high RPM before you start applying any load to them. All right, so what I'm going to do now is go ahead and get this angle right, and we're going to shoot some compressed air in there and get it moving. Now immediately moving itself right off the board. Let's reset that. Again, we can even give it compressed air in the opposite direction. If I can hold the nozzle in place. You can see it's powering itself. We're just not getting a direct straight line because of what I have to run it on at the moment. Let's go ahead once again here. Try to get an angle so you can see it and give it some compressed air. As long as I'm hitting in that hole, you can see that it's creating plenty enough startup torque to move our little vehicle immediately. There's no delay whatsoever. Alright, so if you watch the center drive shaft in this next few shots, and you see that as it's rotating, it starts to slow down, become still for a brief moment, and then reverse in direction. That means we've actually matched with the RPMs of the motor the frame rate of my camera. And that frame rate of the camera is 60 frames a second, meaning every time you see that happen in a single spin up here, we've hit another 3,600 RPM cycle there. The first time you see it happen, that's 3,600 RPMs. While it's still spinning, you'll see it happen again. That's hit 7,200 RPMs, and so on at 3,600 RPM intervals. And I think there was 4 or 5 of those changes in the next few videos, which is well over the 14,000, upwards of 17+ thousand RPMs that we were able to achieve here. Let me go ahead now, add some air to it and fire it up. Alright, so here we go. Let's apply some air. Walking itself around. Look at that, it's moving itself. Well, as you can hear, it's cruising, folks, and that right now is being powered by my invention called the Tromp Hammer. We're getting that air from water running down a hill into pipes. Please look that up to see if we can get it up to RPM. Alright, so here we go. Let's try this again. Alright folks, today what we're doing is we're changing the dynamic of how we're testing our Tesla turbine for aircraft engine use. And right now, even though it kind of has a helicopter look to it, what I'm more interested in is, can the Tesla turbine function as an airplane motor and something that can power your aircraft prop around? So we've got a nice bend now to our prop, so we're going to be turning a lot of air with this prop, especially at these RPMs. Hopefully in these tests today, what we're able to see is that we're able to turn this prop under load up to 3,600 RPMs with 100 PSI and less in less than 2 seconds. Here we go. So that reversal you just saw was us coming back down from a 3600 RPM revolution span there, because that's the frame rate of my camera being 60 frames a second. We know that when we see that in the frame rate there in the visuals. That is so cool. At 80 PSI. PSI. Start out here with a higher RPM. Let's take a look. That is so cool. That was pretty cool. And now there it goes. So today what we're going to do is test our homemade advanced design Tesla turbine. We're going to run that through an electric motor with a gearbox head on it, which gives us basically a transmission through the system, which you saw me use in the vehicle demonstration. Right now the output from that gearbox head is going into a stepper motor. This stepper motor only has the potential of producing a max of 0.36 of an amp. Which is very little. It's going to give us about 20 watts at the max voltage we're going to produce out of it. It's nowhere near the max output that's coming out of this output shaft right here out of the transmission. We're going to need to find a bigger generator. I looked all over. These were the best I could find. I found 2 of them. The other one produces a little bit higher voltage, but exactly the same amperage. We're going to go ahead now and fire this thing up and give it a test. So here we go. This is a voltage test. Later we'll do some amperage tests. There you go, folks. That was going to be the max voltage we're going to be able to produce with our Tesla turbine. We are running at about 100, 105 PSI on that test at the max, and then going down from that pressure. PSI. We are now at 50 PSI. We're now at 40 PSI. And we're about down to the 12 volt. And that'll be 38 PSI, 37 PSI, and we hit the 12 volt marker on that. So we're now set up to measure the amperage. We have the meter set up to amperage. We have it wired up to this AC light. Like I showed you, our voltage is only going to be right around 50 volts, so we're less than half of what this light's going to need to be to light up, I think. But we are going to use it for the resistance to test the load. Let's go ahead and spin this thing. from here we don't gain any more amperage. All we're going to be gaining is voltage. The faster that gets going. So as long as we can get it to the same RPM that we had before, so what you saw there was 54 point something volts with that 0.36 of an amp. That's going to give us really close to the 20 watt or right around the 20 watt range. And with the very small volume of air we're putting into this system at the pressures we're using, that's a pretty good output. And you can see by the wobbling and everything that's taking place that we have a lot of loss also taking place, just not being perfectly balanced. Alright, before it gets too dark, we're going to run this a little bit later here so you can see the lights light up. I put a different generator on there. For now, it's got a little bit higher of a voltage output, so we'll get closer to the 100 volts. It's about 60 volts, 62 volts on the output there. So we're getting closer to the 110, 120 it needs to light up fully. But you'll be able to see that all these little monofilament glass light bulbs that are inside this rod will light up here a little later on with the Tesla turbine. I just wanted to show you that before it got dark. Alright, so we got one final test here for tonight. It's nice and dark. I got the meter now wired in line with the light, so we're going to take a nice amperage reading while we're doing this. So here we go. There you go, folks. Once again, you can see that that amperage stayed at the 0.35 amps. Didn't go any higher. The only thing that was going higher is our voltage.